Alrighty, let's get going. Very, very excited today. This is going to be a really great webinar. My name is Greg Paulson, and I'm really excited to have this panel with us. And today we are going to be talking about everything you need to know about vapor smoothing 3D prints. Uh, Let me tell you, it's really cool whenever we work on these new technologies, especially with industry experts, and we're able to do these webinars. And this is no exception here. Today, I'm joined with Luis Vogar and Brad Dermott from AMT, and combined, we have over 35 years of experience in applied additive manufacturing. And we're going to go through the introductions of us, and then we'll go through our agenda and get started talking about vapor smoothing here. But yeah, let me introduce myself. My name is Greg Paulson. I am the Director of Application Engineering at Xometry. I've worn many hats, being a buyer, a designer, and a supplier of additive manufactured parts. I've worked as a professional in additive manufacturing since 2007. I've ran machines for many years through my previous career, as well as at Xometry. And my experience also includes other processes like molding, machining, sheet metal, and the quality assurance requirements that you need to actually deliver these parts and ensure that they are right. I love talking shop, DFM, applications, and I'm really here to work with customers and help them choose the right process and engineer real solutions. Next, I want to introduce the team over at AMT. So we're going to start with Luis Volger. And you should be able to turn the camera on now here, Luis. And Luis actually is really cool. So I met Luis when I was out at ISAT at JMU, but he is a professional in additive manufacturing for longer than all of us combined here. But he has extensive additive industry experience with materials, process engineering, business development, and management. He's part of AMT's executive team leading the company's growth in the USA. Luis has driven advanced materials and additive manufacturing innovation at companies like Nike, as well as the team at Paramount Industries, which was acquired by 3D Systems. He works in defense, aerospace, wearables, medical, consumer products, you name it. And he's also outside of 9 to 5. He is a member of the additive manufacturing user group. He's actually the chairman and holds a whole range of additive technology patents. Just a powerhouse when it comes to additive knowledge. He had a BS in material science from Virginia Tech and MS from my alma mater as well in integrated science and technology at James Madison University. So really exciting to have you on, Luis. And also want to introduce from AMT, Brad Dermott. So Brad, over the last 5 years, Brad has built his additive manufacturing career with companies like AbbVie, Midwest Prototyping, to understand the needs of the industry. Brad currently grows AMT by matching customers with solutions that drive product development and acceleration into the industry. Brad has a BS in industrial studies with an emphasis on manufacturing technology management and a minor in product development at the University of Wisconsin-Platteville. So again, Luis, Brad, thank you so much for joining. And this is, it's just very exciting to actually talk about vapor smoothing and just additive in general here. So what we're going to talk about today is everything you need to know about vapor smoothing. And on our agenda, we're first going to start off with there's a problem statement. Why do I need to smooth these surfaces anyway? So we're going to go through some of the surface fitted examples of additive manufacturing components. And then we're going to introduce chemical vapor smoothing, go through some of the technical aspects of it. We're going to talk about the benefits, like what does this do? Like what is it really doing for me? Talk about some of the safety aspects. And finally, we're going to finish off with the materials that can be smoothed, as well as the cost of design considerations. The great thing about this webinar, we are doing this live. We have opportunities for you to ask questions as well. We're going to try to reserve the tail end of this webinar, about 10 to 15 minutes for a live Q&A. To ask questions during this webinar, please go to the questions tab. So you have that little tool at the side of this event here. And you can ask questions along the way. We'll try to answer as many as possible. Even if I'm not able to get to those, I'll make sure that we address them after the webinar as well. So please feel free to ask anything and everything. So let's just jump right into this and talk about the problem set. So 3D printed part surfaces, there's a problem here. I am growing these parts. I am growing them with additive manufacturing method. which unlike cutting them down from a solid blank of material where I use a smooth tool, leaves a smooth surface, I have a smooth part, I am taking a material that's lesser, like a filament or a powder, and fusing it up in order to create those parts. And inherently in that process, I'm building small gaps, surface roughness from a powder to powder interaction. And there's ways to introduce either things that can cause mechanical issues or even surface porosity that can cause issues with cleanliness, healthcare requirements, etc. And what have we been doing for the past 30 years about this? Caveman stuff. We've been sanding. We've been coating with epoxy and then sanding. We've been doing something like vibratory media tumbling. So, and that's actually something that we still do here at Xometry, and we have the technology, but it can only do as much as the media can do, and it only takes down the peaks, but the valleys still remain when you're using the vibratory finishing process. And to kind of show you a close-up of what additive parts typically look like, they're not ugly, but again, the surface can still be a consideration here. So this is about 1.5 inch tile of selective laser sintered parts here. This is actually part of our sample cube that we have at Xometry here. And this is made in selective laser sintering, which fuses powder material together. Both SLS and another process called HP multijet fusion have similar results, where the outer surface of this in a natural state feels almost like a sugar cube on the outside. So although the material is solid on the inside, that outer surface can still, have some issues to it, including like if you have greasy hands, they'll take your fingerprint right on the edges too. Also, another thermoplastic 3D printing process, maybe more common to you because you may see this in a desktop 3D printing method, and we use Stratasys Fortis machines in our shop as well. But this is fused deposition modeling. So you can see here this 1.5 inch tile. I'm running at about 10,000 layers, and it has really coarse features. You could even see how those layer by layer basis, it's not a true fuse. It's very good mechanically, but there's introductions of micro gaps and where stuff can kind of get in it. It's not a sealed surface. I've done videos before where I've shown an SLS can and a FDM can, poured water in. SLS will hold the water. FDM will just, leak out on the sides there, because although you can't always see where those gaps are, they do exist. And this is where I'm going to bring in this team here and talk about chemical vapor smoothing. So it's a very different process than what we've traditionally been doing, where we've been doing the physical processes, our coding processes. And I'm going to pass the mic on to Brad here, I think, to just talk about what it is. So Brad, what is chemical vapor smoothing?
Yeah, thank you, Greg. Thank you for the intro and kind of painting a picture of what we experience traditionally when it comes to post-processing. And, as you mentioned, a lot of it is very labor intensive and limiting, whether it's the process or the media size for tumbling, for example. But, there's a lot going on the surface of a printed part. The technology is great, but when you start really peeling back the layers of what's involved with printing, there's a lot that we can fix and improve upon on the finish and on the surface of these parts. And so what vapor smoothing is taking that final step of fixing that surface and removing blemishes, the crack initiation sites, the roughness and everything. And how we do this is we introduce these parts into our closed loop system, and these parts are being processed in a very controlled environment. And in that controlled environment, we're ensuring condensation on the surface of the part with our carefully selected chemistry. And the reason we do that is the condensation is actually putting this as printed part or rigid plastic into a flow state just on the surface. And that flow state is where all the magic is starting to happen. We're starting to loosen the sintered part or the fused filament or something like that, loosening that up, and it actually starts to flow, like you can see in here in the image. And a lot of those peaks that you mentioned are now, instead of being removed or shaved off or sanded down, we're actually moving them down into the valleys, and that's what's making them smoother. And at the same time, we're actually sealing the surface with that material, whether it's PA11, PA12, ABS, whatever that thermoplastic is, we're smoothing and sealing with that same material. And then we have to carefully stop that flow state before we start rounding out features. So that, again, is very important when we control that process as well. And then we actually re-harden that polymer and extract the chemistry out. and at the end you have a completely processed part with no added or removed material. And I don't know how many of you out there are familiar with the DIY acetone process of vapor smoothing, ABS mainly. It's very similar, but what we've done here at AMT is take that very kind of backyard approach and brought it into a very controlled, automated type of system to allow 3D printing to grow into this production environment that we want to take this type of finish into the industry.
Yeah, and I'll definitely add there why this is important, because you're absolutely right. Like I think a lot of times people ask this is acetone, and first off, I could put nylon and acetone and it just kind of takes a bath. It's fine. It's fine in there. Like a lot of these materials that we're talking about from Selection are just very chemically resilient. They're pretty robust against a lot of chemical exposures. So having something that can actually smooth out that material is pretty unique in itself. And also the acetone processes tend to have mixed results. And it tends to be more aggressive from the get-go. So you can have over smooth parts and sometimes even like dripping parts of their own plastic afterwards. So this is a much more repeatable, much more controlled process. And as a provider at Xometry, like my goal is, when my customers order parts, I am here to deliver. I have skin in the game here. I'm here to make sure that the parts are a success. So when you have a controlled machine like this Post Pro 3D, it really takes a lot of that guesswork and science project out of it. It makes a very repeatable process for you from a production standpoint as well. And I got some examples here, just kind of showing some images. And actually, these are some of the X's behind me here. But this is Selective Laser Sinter. And the item on the left is a vapor smooth piece. So the surface, you can see it's not polished, and we try to stay away from the word polish for a few reasons. But it is, what it's done is it's sealed that surface, mitigated a lot of the coarse layer features to it. And even when you feel this, it feels like a molded plastic piece. Like it has, you don't feel that surface roughness on it. Compared to on the right-hand side here, this would be a standard finish, grow, clean, and ship. And this has that much more matte sugar cube-like feel. The one caveat I'll say is that these were actually built at different times. I built these at different orientations. So I like this orientation better. I built this afterwards, and that would actually mitigate a lot of those lines there. So this could be even smoother if I built it on the corner like I did with this one here. And yeah, if you want to talk a little bit about these parts too. So these are some examples as well. And what's neat is, we're showing some rigid parts, but also some of these have elastomers, right?
Yeah. So the top two parts that you see, that kind of tubing and the cushion, that is a flexible material printed on an MJF printer. But the benefit of not only taking a flexible material but chemical vapor smoothing is that we can smooth and seal the material, but it's a non-line of sight process, meaning we can get the inside of these complicated lattice structures or through the through hole of this flexible tubing with the chemical to evenly smooth the inside and the outside of the part equally. Where if you were to do this traditionally, good luck trying to get your hand inside the lattice structure to sand it, or inside that tubing to sand completely, and then just to smooth it, right? And then you would want to add a coating to seal the surface. Well, vapor smoothing does all of that in one step. And then the parts on the bottom here are also vapor smooth. This is more of a rigid plastic, and that's again printed on the same technology. But you can just see the level of the appearance on these parts are just bringing it to a whole new level as compared to as printed parts.
Yeah, absolutely. And usually we're going to save some questions at the end, but I saw one that was just right. Like I already saw questions coming in. This one's perfect, which is talking about that non-line of sight. So how's it handle interior surfaces? And Brad, you just nailed it. When you have, because you're condensing the solvent, the finishing agent, and it's condensing all over the part, like it covers all surfaces and does the work. And it's pretty amazing. And actually, we were doing some tests with some closed off tubes. And after we finished smoothing, I actually took a flash on the inside, and you see a reflection, or you see you see a reflective out, and you're like, oh my gosh, yeah, this actually polished the inside of that feature as well, which is just something traditionally is extremely difficult to do right. Yeah, and
Exactly.
that's a great segue here. So I'll let you all talk about a little bit about this, but yeah, just what are these benefits? Let's go down some of these benefits here. I think sealing is a big deal. So let's talk about why is sealing a big deal here?
Yeah, no, I mean, there's a long list of benefits. And when it comes to a sealed surface, it can be absolutely critical for some applications. We had a really cool case study that was looking into a vehicle's intake plenum, which is part of the intake manifold. And this plenum acts as like a pressure chamber. So it was extremely important to be light, strong, and sealed. So the race team used 3D printing to make the light and strong piece. And then they used vapor smoothing to seal the inside and outside of this plenum because any leak of air or in or out can sacrifice the performance of the vehicle's engine. And so taking the, in this case, nylon 6 with chopped carbon fiber into the material gave it really, really good strength. And once they added vapor smoothing, two things happened. They were able to meet the requirements they needed for this application, but they also didn't have to add additional costs for labor for sanding or coating this component. And once they were completed, they actually, pushing the boundaries of 3D printing and bringing in vapor smoothing, they outperformed all previous years that they've ever raced with a component like
Wow.
this. So it really changed the game for this team. It was a really cool application.
And what
And
about,
then,
oh, yeah, like I was gonna say, this is the surface finish, the sealing. Like, what about performance? Like, do you have any examples? Why is the performance improved? It's not always intuitive, right? Like it's the same plastic, but like why can I stretch it more now, or why can it take more flexes before breaking?
yeah, the main reason is what's happening on that surface is those peaks and valleys are evened out, and some of those valleys tend to be crack initiation sites in the powder technology, which is a point of failure if it's exposed to different stresses, or the separation between layer lines in filament printing, for example. That's always going to be the weakest spot, is in that Z direction because it's not actually melted together completely. And so what vapor smoothing is doing is removing those flaws in the surface, removing the layer lines in FDM, and actually creating almost like a skin on the outside of the part that creates a much stronger outside. So now we're able to improve elongation at break because these failure points have been removed, and also maintain tensile strength, and in some cases even increase tensile strength. So now we're taking these carefully engineered materials and elevating them to new heights just because of vapor smoothing them.
Awesome, awesome. And I think that's that you mentioned this going on to, for no extra coatings. I'll take an example. Oftentimes I would epoxy coat something to create a sealed surface and smooth it out. Uh, one of the one of the challenges, the downsides of epoxy coating is it could be UV exposure or just a natural weathering. But usually it looks like your part is two layers. Like whatever's underneath stays as color, and then what happens on top starts to yellow and brittle at a very different rate. And by essentially just reforming the surface using this technology, it you don't have this weird color differentiation. That happens, by the way, if you like put a clear coat on your parts too. You see that weird thing happen. So it really does have a benefit, not just for immediate use, but even over duration. That's something I've noticed a lot is my parts that I've used for end use, that I've done secondary processes over the years, just they don't look right. They may work, but they don't. The cosmetics are just gone. Um, we talked a little about the closed loop system, and I think this is important for as a manufacturer as well because it allows us to essentially have a safe work environment. This is very different than like flammable acetone vapor, for example, working this. And the whole system is downdraft. Just for the sake of time, I don't have the video in here, but I had a video of showing how it's being opened up and how we're handling these machines. And they're pretty behemoth machines working with, but all the vapor is actually uh, dissolved out and reclaimed within the machine. So for us, we're just responsible for essentially exchanging the canisters, and I know AMT takes care of the secondary material, and we ship it back for you to take care of. So it's actually very operator friendly as well. Um, Now, can you tell me a little bit about dimension accuracy? So I am kind of reforming some of this part, but like, what do you see? What do we see with a dimensional accuracy with vapor smoothing? Say either Luis or Brad. I'll voluntold you.
Luis, I think you're muted.
Hold on a moment here.
Yeah, so
Brad, I'll jump in.
so what's happening as far as dimensional accuracy, and I mean, yes, we are reflowing the material on the surface, but it's such a small amount. What we've seen when measuring before and after, it really is nominal. It's not really making much of a difference, and even in some cases, we haven't seen a single change in the accuracy of parts, depending on material. And when it comes down to the actual material and further in, I think Luis can shed some more light on giving you a visual of what's actually happening.
Yeah, absolutely. Luis, I got you.
Yeah,
I
thank
got
you.
you on
How is that?
mute.
That's good. Thanks, Greg. Um, yes, as far as dimensional accuracy, it's critical. It really is the only product in the market that can claim full control of the dimensional accuracy of a part, and that is because we are controlling all the different variables of the process with uh, a highly engineered piece of industrial equipment. So, when it comes to dimensional accuracy and different examples that we have, I mean, think for example, many of you may be familiar with cushioning components for footwear, right? These applications are examples of where the wall thicknesses of the geometry must be consistent, and they must have a very uniform set of properties in order to respond according to the expectations of the product. So when it comes to that particular example, the requirement could be to meet a plus or minus 0.5 millimeters of tolerance in or better as far as the wall thickness. So how are you going to do that when you have a surface that could have 150 microns worth of material on each side of that wall? There is nothing but just roughness. So you have to do it very carefully so that you don't damage the components, and so that you do it also um, on the outside and the inside uniformly. You can't treat just the outer portions of think of a lattice structure, for example, like the one that you saw in previous slides, uh, versus the inside. You can't have a line of sight type of challenge where what gets hit first with the vapors is smoother than the internal property. So there lies the challenge of the technology and us being able to control the flow of the chemical vapor in an automated way.
Yeah, and I'll put a tidbit as an operator, machine operator. So what we call these recipes with this machine. So depending on different geometries that you're using, as well as the process and material combination that you have, we have different recipes based on what we're racking and what we're making to help control some of that. But what's nice in the machine is it's a machine. It's operated. It can control the cycles, the pressure, the heat, the amount of solvent used. So it allows you to really tune to a particular process. And even if we have a geometry, like for example, I have some bulky FDM prints that we're trying to remove a paint step from. We just want to print it in yellow FDM and smooth and say we're done, versus printing, then sending out for someone to essentially sand, prime, paint, and you're adding hundreds of dollars per print. And because they're bulkier, and this is more a regular job, we're actually going to make a little custom recipe to make that work for repeat orders as well. So there's really cool solutions, and I'm going to highlight that as also improved cosmetics, improved color. Can you just take a step that adds hundreds of dollars in 5 business days out of? Yeah, you can with this process. And Luis, actually, I think, and I think that was my fault on the mute there. So, but I think it's
No
good
worries.
timing. This is the next
Yes,
question, right?
absolutely.
Like, is this safe, right? So we're talking about vapors. I use the word chemical a lot here. Is it safe, and can we walk through some of that?
Yeah, absolutely. And I think you did an excellent job summarizing some of those benefits when it comes to the improved cosmetics, the improved performance. It's really an excellent way to just think of a different way to use 3D printing as we have been using it today, especially when you start think of the ability to put colors on a medical part on the fly as the product is being manufactured, right? Those colors and those parts are not only have to be vibrant, and you have to keep in mind that they are going to come into contact with a customer. Sometimes you could be 3D printing toys for kids. So the question lies, okay, well, we're using a chemical vapor process. Is it safe? The reality is we are using a chemical. It is a very safe chemical, but it is a chemical, and therefore it has to be handled with tight controls like the ones that we have with our equipment, and also has to be tested. The ultimate product has to be tested, not just the chemistry. It's one thing for us to be able to guarantee that this chemistry has a set of certifications that will guarantee the safety, environmental safety, and industrial safety. But it is a very different requirement as far as the product goes. So, some of the requirements that we've summarized in this table are based on the applications that we've typically seen, and I'm sure a lot of your users and a lot of the attendees in this panel are wondering about. Is it safe to use to meet food contact requirements for certain applications? Food contact is one of those that many of you may be very familiar with. It's used just globally to make sure that the food is not contaminated by the product it comes in contact with. So it is very important to understand that our process does not provide automatic approval for food contact applications. Food packaging testing and contact materials testing is required for the specific product, the material, the design, and the operating conditions of it, to ensure that your products will comply with the appropriate regulations for food contact material.
I'll always say food is an application. As an application engineer, that's something to note, is that food is an application. So it's not just the material. There's a lot of FDA approved materials and USP Class 6 materials. But food is also the intention behind it. Actually, food contact has to do with design for cleanability, design for access, and there's a lot that goes into that. But I have a whole post on 3D printing for food safety products, and it was actually very nice to actually revise it when we added vapor smoothing to that point, because we could actually be like, yeah, look at this, we're improving that. So I have to throw that in because it's so interesting how it combines. Yeah.
I agree, and sometimes even the material may be approved for food contact. The post-process also need to be considered, right? And in this particular case, the test that we're presenting was for SLS nylon 12, but it was for a very specific application of a part that was going to come into contact with food, and the requirement was to pass a 2-hour under 70 degrees Celsius exposure. And there is a big handbook with many different applications of food contact and just the requirement in testing to pass. So we have a lot of experience going through the gauntlet of interacting with the different accredited laboratories to pass and to test for. So if any of your customers are interested, or if the greater Xometry is interested in any of these particular applications, we always welcome in the collaboration and the partnership. You'll find out that most times we may be even willing to cover the expenses of the testing, or share them with you. So because it's just for the sake of creating this knowledge base for the industry as a whole.
And absolutely, and I think that's something that's really important is that we, not only use this for, although it's very accessible, it instantly quotes online as you're developing your product. Xometry, we have this entire marketplace, and we are connected with so many technology providers, including the folks here at AMT, to help really leverage and bring your design to the next level. It's just really exciting. I want to jump to the bottom two though, because I will say like food contact is an application where it's by adding the smoothie, the surface uh, um, this surface sealing. It's a really big deal. Like I know skin irritation, cytotox, especially skin irritation. It it passes, but I can also have standard SLS pass because it's a pretty neutral material. But especially those bottom two. What do I have bacterial growth in my parts? I can tell you right now if I give an FDM part or a SLS part standard finish, and we do this test, it's almost an automatic fail to it. So seeing this pass on the MRSA and E. coli test, for me, like when I saw that, that's very, very exciting as an engineer because I just couldn't do that with this process. It would just be a non-starter. But just talk about like why, and actually I saw a question that I'm leading to as well. Why would you see a reduction in bacterial growth for something like MRSA or E. coli on these smooth parts, vapor smooth parts versus the other? Like what are we like what are the considerations there, and why does the vapor smoothing actually improve that result?
Yeah, I mean, great question, and great segue. In coming from the skin irritation, I think when it comes to the bacterial growth, certainly just to give the audience some context, we started. As many of you learning about all the potential applications, and for skin irritation we had consumer products, right? That you're talking about wearables, jewelry, sunglasses, racing and sport protective helmets, 3D printed fabric in some cases, things that are coming into contact with your body. You have medical applications. When you start looking into medical, that's where, I'm talking about splints, prosthetics, or orthotics, for example. You get into a range of applications that not only requires you to, they are not only parts that are coming into contact with the skin, but it's also parts that have certain set of requirements for keeping and maintaining, ensuring the cleanliness and the ability to sanitize them, the ability to sterilize them. And when you have a surface porosity, any 3D printed part, no matter, and this, whether it's from a filament type of process, extrusion-based process, or from a powder bed fusion type of process, you are dealing with microporosity. On average, you are going to see 10% porosity on the surface of a part. That microporosity, we're talking about cavities that can be, anywhere from a 10 micron to all the way to, 150 to 200 micron cavity on the surface.
This image on the right here, right, is the would be the unprocessed of a powder bed, which is pretty it's very inviting if you're a microorganism.
Oh, absolutely. When you most of us that are familiar with 3D printed parts know that the part coming off the printer after cleanup and support removal, sometimes can have a very good resolution and it may feel very smooth actually. But when you look at it under the microscope, the reality is that there is a significant amount of porosity that is not observed by the naked eye. So that microporosity is where all the microbes thrive. And to address the question of why this process, what is the big deal, what is the value add from this process, really is that ability to seal that microporosity, as Brad explained, and get rid of the environment where these bacteria can grow. So you're absolutely right. The material may be qualified as having all these excellent microbiological certifications, but it certainly is not an injection molded product, right? We're not dealing with a part that is fully sealed. So, and that can be, for any of the materials that are available in the market or out of any of the processes. So that's where our process really shines, because it's not restricted. It's really agnostic to the process, the materials. So we have had the fortune to collaborate and to closely work with the applications engineers from essentially every single material manufacturer for the 3D printed industry. And some of those that you're showing on the screen, and
Yeah.
some that we cannot share, but also every OEM. Because there are a lot of materials that are in development, and we support those efforts too. But every single OEM is looking at this technology as an enabler, not just for performance, but also for being able to remove the time to the readiness of a printed part. So
Yeah, and I was going to say, like, just one of the things we look for at Xometry is something that floats a lot of boats, right? When we look at adding on technology, and that's what we really like, is because we have 8 additive manufacturing processes, and the 3 of those are thermoplastic direct manufacturing, and then we also have, like, our thermoplastic photopolymers and metals as well. But to be able to actually essentially affect almost all our thermoplastics with a single process is really cool. And actually, I'm gonna jump to the next slide here just to kind of show this a little bit. Is um, from our listing at Xometry that we have for selective laser sintering. So that's one of our most commoditized manufacturing platforms in additive. We're instantly quoting vapor smoothing on nylon 12 and nylon 12 glass bead. In HB multi-jet fusion, similarly, nylon 12, nylon 11, nylon 12 glass B, and TPU are all now instantly quoting. And what's really exciting is that we do have all the entire Fortis line of FDM, including of course you have the commodities ASA, ABS. You have things like static dispositive materials, polycarbonates, and I'm personally excited about Ultim, the ability to take this very strong, very chemically robust material, like an extremely high performing material, and actually seal the surface on it, because that's usually where we run into some issues. Is I need a high performance, high temp material, and it needs to hold air, and it needs to do X, and without the ability to be sealed because of those micro gaps in the surface, that's sometimes an application that does require some creative coatings to figure that out. And being able to seal that surface is just very, very exciting on this. So I have coming soon, because it's not instantly quoting yet. But when you look at SLS and MJF, I call these 90% tools. 90% of the time, it's probably the additive process that you're using. So to be able to actually instantly quote this, and you'll see like this process. Actually, I think I'll go one slide back here. But this process, because it is a racking method, I'm able to array multiple parts at one time. You also have a much more amortized price, so it can be cheap to add vapor smoothing to these commoditized processes, because I'm building so many parts all the time, in like nylon 12, for example. And just something to note, and kind of behind me, it's probably a little screen if you're watching this webinar here, but I got some colors behind me. But this is actually this is SLS nylon 12, and you can dye parts. So after these parts are vapor smooth, we can use acid-based dyes, and so I have red, black, green, blue, yellow, and again, that's something that we quote. And yes, I love my workbench in the back here, and of course, with our other processes like MJF. Since it's a grayscale, you can usually just do a dye black. But even when you vapor smooth a MJF part, which would be a kind of like naturally light gray surface, it does significantly darken the surface. So you can see here kind of how the surface is darkened from a smooth MJF part there. And just like anything else, we're building parts that are designed on purpose, right? So we can do post-processing, adding tapped holes, adding inserts, etc. But I really, I put this slide back up here just to emphasize this process is repeatable, it's scalable, it checks those boxes for what we want to do when we want to provide for our customer a repeatable experience. You could get this part, order one today, 3 months from now, or order 300 more, and you get this, you get the same experience. Because it's not a science project. It actually is a tuned, recipeed device that we could run parts through. It gives a very consistent, repeatable production experience. So it helps really augment that as well. So let's jump in the design for vapor smoothing. And by the way, please keep the questions going. I've actually seen a bunch of questions, which is really exciting here. Jumping up on my screen, we'll try to get to as many as we can. But let's just talk about some design considerations for this. And I know, Brad, I'll let you kind of lead into this a little bit, but we actually rearranged this because I thought, ooh, add radio is a big one, but like uniformity. And so, yeah, why is uniformity so important when we're designing to optimize for vapor smoothing?
Yeah, no, absolutely. I mean, luckily with 3D printing, you have a lot of freedoms to design. That's the benefit of this industry, right? You have a lot of freedoms, and if we can start kind of solidifying what those limits would be for vapor smoothing or parameters per se, making an equal wall thickness or even thickness throughout the part is a big benefit to vapor smoothing because it is a thermodynamic process. So that carefully controlled environment that I talked about in the beginning, all of that is to ensure condensation on the part. And if there's a variation in thickness, you can see a variation of processing simply because this vapor wants to get back into a liquid state. The easiest way to do that is to cool off, and thicker parts tend to be cooler for longer. So if there's a wide range of thickness on a part, you can see a little bit of a variation in the smoothness of a part. So that's why uniformly creating a thickness on your part will give you a much more even finish throughout the entire part.
Yeah, and I'll even say these are samples I made here, but if I had a shell command on that side, because I kind of have a thick portion where the X is here, I probably had a little bit of improved results consistently on this, but actually I mean it came out still pretty well. So it's forgiving, especially on SLS. It's pretty dang forgiving. Yeah. But you can always, if I made these for samples, but if I'm making these for production and I'm looking to do a repeat, there's that little bit of tuning is going to go a very long way in managing your quality and expectations.
Yeah, a lot of it's the extremes, right? Like if you were to have like a large block of like 1 to 2 inches or something, and then you have the complete opposite of a 1 millimeter feature coming out, really hard to evenly coat a part like that. And just kind of from 1 millimeter mark, just to segue into the next point, the reason why we want to keep features above 1 millimeter is for a number of reasons. That's starting to approach some limitations of printing if you go below. But when you are hitting 1 millimeter or below, it doesn't take a lot of energy to fuse those few layers together in powder bed, for example. So that feature becomes almost like a sponge for vapor smoothing. So the vapor will move into the surface and just kind of hang out. There's not enough material to actually grab and start moving and pull together, which we can on all the other surfaces. And then when we extract the vapor out, it just comes right out of that sponge. And it essentially, if you get too thin, nothing really has happened because of the very high porosity. So that's a reason why 1 millimeter is highly recommended of staying at that minimum thickness.
Yeah, and something I want to note here is that this is a smoothing process. I think some measurements I saw, the typical RA value is going to bring it down to about a 63 RA, and that's kind of a measure of like if you took like a kind of a record needle and drag it across, and you'll get that up and down, and that's your variation of RA. But if you look at these parts here, they're not being polished, and if I do have more coarse layer features on this, they're going to be present but heavily mitigated. It's just something to note from a managing expectation standpoint. It still looks great. It kind of reminds me of what I would call like a semi-gloss texture to a part there. And I'm going to jump to the racking requirements. I have a slide just kind of showing what that looks like. We do have a decent sized chamber for this. So essentially everything that's auto quotes for you right now for SLS is about the same size as what this chamber will accept for smoothing parts as well. And we want to be mindful. Usually, if you have a large, bulky part, we're going to take a look at that probably more with more care about smoothing those pieces. But there's a lot of room for us to put a lot of parts there, and that helps kind of share the share some of the wealth, if you will, when we're running through this this production process, and you'll see that reflected in pricing as well. So they are suspended though. I am using a racking process. If you're familiar with CNC machining sheet metal, I'm hanging pieces on hooks and going through a dipping process. Very similar setup in this, except it's open air, not a dip. And I am going to have to hang parts somehow, some way. So if I have a part like this X tile here, which is the flat piece, we're going to probably use an alligator clip to hold those in place. And on more rigid materials, you'll see these little, usually 4 little little clip marks there on each side of it as it bites in. It'll be pretty mitigated, but it's something that needs to happen because we need to, make this have this hanging somehow, some way. If you do have a through hole, you're gonna see that possibly a slight hook mark where we find a hole to actually hang the part on. And that hook, or sometimes we just run a wire through if it's a longer hole, for example, and you may see a little nub on one side and the other where that hook or the wire is touching. But we try to keep that as minimal as possible. And from a design standpoint, especially if you're working into production, you may be able to introduce a feature for racking as part of your design, especially with 3D printing, where you could just put an eye loop or something out in a random place, not worry about design for manufacturing considerations, because you could just do that when you're printing something like MJF or SLS. So when you look at production, you could get a little clever about keeping your cosmetic faces as pure as possible while designing around a vapor smooth process. I did want to note that if I have a softer material like TPU, it tends to have more exaggerated features. So you may see like a bigger hook or racking mark on a TPU material versus something like a rigid nylon or glass fill nylon. So I don't need to ask you this because I'm seeing questions come in. So I'm just going to run through a little bit here, and apologize for the brevity. But just I do want to talk about, we're talking about one portion of your platform from AMT, but just want to talk about what do you all do? Right, what else? What type of portfolio are you working with your machines? And just let you talk a little bit about that for a moment.
Yes, thanks, Greg. Certainly, what we are all about is addressing the main challenge for 3D printing at scale, which is throughput and cost. No matter what the application or what the industry is, it comes down to the ability to meet the throughputs and to meet the price points and the performance of the materials, of course. But when it comes to AMT, we offer an end-to-end solution. We're all about automated post-processing solutions for the additive manufacturing as a whole. And really, our goal is to erode all the barriers that are against the transition to production for a lot of these applications. And that can be just through automation and through innovation when it comes to taking chemistry, engineering technology, and being able to deliver something that adds value. Because at the end of the day, it is a post-process. So there is a negative connotation about post-processing because it's an additional step, and the negative connotation is that it's going to take longer and add cost. So we're very sensitive to that reality, and we see it as a challenge and as a barrier, not just for us, but it's just for the industry as a whole. So you're very familiar with it as the largest service bureau in the industry. And any type of service provider or any customer that is looking at these 3D printing technologies will face the same challenges. Once you get the performance, once you get the throughput out of the printer, the reality is that there is a significant amount of cost that comes from the labor and all those archaic techniques that we're still using to post-process parts. So that's what AMT is all about.
Yeah, I was going to say, and I think a lot of us who have been operators, you will constantly fantasize about machines like this when you're sitting for 3+ hours, hands in 90 degrees Celsius powder, burning them, trying to get a part out, to get to your customer that day, and thinking, man, there's got to be a better way. So I mean, it's just
Absolutely.
dramatic improvements.
That's the fun of it,
Uh,
going home with all that powder in your hair, right? Like,
the best thing of it is I used to wear a lab coat that had a pocket on it, and so after you get all dusty, you take an air hose shower, which is just spraying yourself off with the air hose. And if you got a lot of
that,
powder in there, you'd spray down and straight up in your nose, like just puffed up in your face and your nose. So good.
those were the days, right?
Those are the days. We still look at them fondly, right? Uh, I also wanted to point out that the FA326, this finishing agent that's right now like under all those materials I listed, is able to treat and smooth. You have just released a chemistry that is able to actually affect polypropylene. And if you all know injection molding or essentially machining or anything else, nothing sticks to polypro. So getting that condensation on polypro is really tough, and the condensation is needed to smooth. Uh, I'll just highlight that because I'm excited because we can actually in MJF print in polypropylene, and be able to print and smooth can open up even more entry into a medical device, automotive, and especially food contact devices. So that's very exciting. And of course, I got to highlight that we have a lot of this automated. Our point is to be Xometry is to be the one-stop shop for manufacturing. We use AI and machine learning to actually price out parts instantly. We're using computational geometry to actually interpret the 3D model that you upload instantaneously. It's priced out of multiple processes at once. And even when you add these finishes like vapor smoothing, tap tools, adding dye to this, you're going to see the pricing lead times automatically update. I recommend going on to Xometry, uploading a file, and checking out how the pricing compares between like an MJF part, MJF smooth, SLS smooth, and change some of those quantities. You can even see how the vapor smoothing amortizes over quantities. So it's very exciting. It's a free site to use, and of course, when you press buy, get your part. It's pretty exciting too. I'm a customer, as you can see, and we do offer a lot of additive manufacturing. We just added binder jet, so I need to update the slide, but I have 7+ here. If of all our additive manufacturing technologies, these are industrial AM technologies, and with chemical vapor smoothing, we have a good gamut. All our thermoplastics are affected. I actually saw a question here about can you smooth SLA parts, like accurate parts, but this is chemistry specifically for thermoplastics. Is that right?
That is correct.
Yeah.
This is just for thermoplastics. We do have a chemistry that will be available for the curable materials.
That's interesting. The more you know, that's exciting. Other thing to note is we have some great resources. So nobody knows a dozen manufacturing technologies back and forth. At Xometry site, including if you're looking to learn more about vapor smoothing, we have a page. I have it linked on the next slide here. But check out our resources. Check out our complete guide to 3D printing. If you want to read a novel about additive manufacturing, start there. We have free design guides, and our capabilities pages are very robust per technology. So if you're interested in a technology or you know one really well, but you want to learn about another one that you're curious about, check out Xometry's free resources. They're very good, and they're there to help you make a better design decision and hopefully get a more successful project at the tail end. The other thing I want to note is if you're logged into Xometry, upper right-hand corner, we have a earn credits button, and this is our Give 50, Get 50 program. So if you click on this, you'll get a referral link that you can share with a colleague who may be interested in Xometry. If they log in with that link, they'll instantly get $50 of Xometry credits to actually use against their first purchase. And if they purchase, you get $50 of Xometry credits. So it's a really good win-win there. It's a way for us to kind of expand and work on more projects. We just love making parts. So with that, Q&A. And again, thank you all so much for bringing in the Q&A. And Luis and Brad, this has just been an awesome conversation. I know I want to spend about 10 minutes or so on this, so we're going to go a little over. I know if some of you folks have to call up at 5, that's okay. Keep on asking questions, and I'll get back to every single one of these questions asked. So just please keep on going. But let's talk through. So I'm going to open up the questions tab here. And the first question is, will there be a recording? Yes, we'll have a recording coming out in a few days here. But yeah, I've seen this a few times. How long does it take? So I could tell you on Xometry's website right now, we have a 3 business day lead time, especially as we're introducing this. This helps us kind of mitigate and understand how long it takes per batch and work through. But from the actual process. So I'm done cleaning my parts. I put them in a machine for a standard run, let's say nylon 12 SLS. Like, what is a usual cycle time in an AMT machine?
Yeah, standard time is about hour and a half to 2 hours. We'll say an hour 45 just for sake of conversation, but in that cycle there's three different stages that are actually happening to the part. So there's the processing, which is a very short period of time in the beginning where we're smoothing the part, putting it into that flow state like I mentioned before, and then we need to stop that flow state, so we move into a curing stage, and that rehardens the material and removes most of the vapor cloud that's in the chamber. And then we move into the final step, which is the drying, which takes up the majority of the time. And that drying is heating up that chamber and the parts so we can extract all chemistry out of the materials. And at the end of that full cycle is now a final complete part. So there's no secondary cleaning or processing or drying or anything. The part is done in an hour 45.
Yeah, and actually, I think you segued in perfectly to the second question, which was, is there any residue like on these parts? Which I think you just answered there. The residue is actually essentially absorbed back in a closed cell system on the machine. So when we open up this machine, it's almost an open air system. There's a downdraft apparatus. We're able to just take the racking out, and for us as operators, we're able to have the next rack ready and put it in, get going with a second run. So you could actually do multiple runs per day with a machine here. But I do have a question. So does it affect resistivity? So I think this segues on, Brad and I were talking about this as we were preparing here. We have some materials that are static dissipative, like ABS ESD7. Would that affect my static dissipation from like a ESD plastic, for example?
So far, we haven't seen any negative effects. Some stable and some actually improving the characteristic of that material. No hard testing as of yet. Where that's something that we plan to do here in the very near future. But yeah, we've seen positive effects from vapor smoothing and an ESD material, for example.
Yeah, and I could see that actually possibly improving a CF material, because CF usually this is a nylon 12 CF carbon fill material, and I could speculation, but with my understanding of it, because usually you're flattening down the carbon fibers. So if I take a meter and put it on one side and the other, I may find different levels of resistivity. But if I smooth that surface out, I actually may get some improvements. But that'd be fun to experiment with.
There's a small variation will be expected, Greg, as you know. If you measure the conductivity or the ESD properties of a part before and after smoothing, some of those fibers that were previously exposed now will be under the polymer or coated, if you will, but the part itself will retain the same amount of carbon that is bringing that ESD conductivity. So, but a variation or a difference before and after is to be expected.
Okay, that's good to know. I have
similar. Greg, I think it's similar in, hopefully is in one of the questions there, but for FR properties, like flame retardant type of properties, it's the same condition. If for extrusion type of parts, you won't see a change, but for some of the SLS or just parts from a powder bed fusion process, those additives that are dry blended into the powders and that are on the surface now will be coated with the polymer.
With the polymer that actually is liquefying. That makes sense. I have a question, and this is a good one, and actually goes back to some of what we were talking about as health and safety. But what happens when I put a drop of water on a vapor smooth part? And I'm going to use, for example, again, laser sintered or MJF. And just to let you know what happens when I don't vapor smooth it, the drop of water, instead of looking like a bead, is usually kind of flattens itself out and eventually just absorbs in on that essentially outer quarter millimeter of surface. So what does it look like when I vapor smooth?
It just speeds up.
Yeah, exactly. It just turns into that water droplet that you'd expect if you put it on a table or something, and what you were watching is those big cavities and porosity that we were talking about earlier, and the water's just finding a place to sit. And you know, that's kind of again where the bacteria would grow as well. And so since we're smoothing over the porosity and essentially filling it with the polymer, it's now a much smoother substrate for this water to sit on, and the water eventually would just evaporate. So you can just wipe it off, and that kind of segues into another benefit of this sealed surface is that now you can clean and sanitize parts, and now make something that used to be maybe a one-use a disposable piece now into a reusable component or reusable application because of the sealed benefits of the surfaces.
Yeah, I think one of the things that I think about is actually veterinary medicine, and it sounds kind of strange, but in you know, human medicine, there's a lot of disposables out there. Veterinarians don't always have that, and I've actually seen a lot of amazing additive innovations in creating reusable tools for you know, veterinary surgery, otoscopes, you name it. But still, they're usually using a part that has a inherently rough or porous surface on the outside, so it has more use, but adding something vapor smoothing can actually really expand some of those innovations, and that's my beacon out to anybody who's a veterinarian / engineer to start innovating, because there's some exciting stuff there. I have a good question just in vapor smoothing in general. Is Xometry running the machine? You know, are we running it or are we partnered out? Yes, yes to both. So we have Xometry, we have an additive factory. We have over 20 industrial additive platforms running, mostly around fused deposition modeling and selective laser sintering. And the machine that we have in-house does complement both those technologies very, very well. So we're able to add that service as a value add. That being said, from a manufacturing marketplace, which Xometry is, we're connected with thousands of capable manufacturers, both domestically and abroad. We're able to partner with suppliers who also have these machines. So that's how we can expand into more of these materials. When I'm talking about the multi-jet fusion materials and beyond, we're actually able to expand out and reach out to our partner network and add materials and finishes beyond our current site that you could then just access directly with a click, drag, upload, and buy experience. So as we expand our marketplace, we are able to bring the capabilities and talent of these operators and their services and become a storefront for them as well. It's very exciting. I got a wow factor on Ultim, so I'm just going to give a shout out to that's something, you know, we're very excited as well. And let me see. I'm gonna, just for sake of time, I'm gonna find one more question here. A lot of these we've tested. So actually, on the non-line of sight, is there a depth limit or something where you from a design consideration where you should put like as some sort of entry or something like? So I know when I clear material out for bead blasting, I want to have an exit hole. For a non-line of sight feature, should I have an entry and exit hole, or does that matter with a vapor fusing?
Yeah, when it comes to vapor smoothing, if you're already designing that into the part for depowdering, it's best to keep that consideration as well. The key is efficiency and being able to make the smoothing as efficient as possible. Creating a through hole would do that. A blind hole is a little bit more of a challenge just because we are processing these parts in a negative pressure environment. So we are removing a good amount of air in the chamber, but some of these blind holes, depending on orientation, it might stay trapped. So there could be an air barrier for the vapor. So orientation, not only in the processing chamber, is just as important as the way you orient it in printing as well. And making sure that the direction of those blind holes, for example, are facing up or something like that, so the vapor has a much higher chance to move into a more challenging area like that.
That's awesome. And I have so actually I want to end this this webinar with a little bit of possibilities because this is out there and something that's kind of exciting for me as well. And again, like we have, you know, technologies where this has really been focused on additive, because the biggest problems for additive manufacturing has been the inherent surface finish and how that can affect anything from mechanics to performance to just where I can actually apply it successfully in a production viable method. But the question comes out: can this be used in polymers made outside of additive, machine pieces, machine polycarbonate, injection mold. Is this technology viable for smoothing those parts as well?
Absolutely, yeah. It's it's something that is not limited just to 3D printing. It can work very well for thermoplastics. Interestingly enough, it could actually work also for some acrylated chemistries that are not 3D printed. Whereas this, so molded parts and extruded parts, parts that are coming from CNC machining, all those witness marks from end mills, all those parting lines from injection molds, all those ejection pins from the injection molding machine. All of those things are things that we are able to erase in a very affordable and quick manner without introducing a whole lot of cost to the part.
Yeah, it's very exciting. I can actually think so when you do polishing of machined plastics, remove mill parts, particularly for things that are clear like polycarbonates or acrylics. There is a really nasty chemical method where you kind of have to be in this well ventilated tent, and you just don't want to be near it. And that's kind of been, again, this ongoing theme of how else have we vapor polished stuff in the past. Another way is flame polishing, putting your part that you may have just invested thousands of dollars of machining work in, and then putting a flame against it, and just hoping you're not standing there too long to accidentally cause a scorch. And having a more controlled method is very exciting, and again, it's future forward, but it's something I'm really excited to talk about. Again,
Yes,
Brad,
absolutely.
Luis, this has been fantastic. I'm really excited about having this added to the portfolio for our manufacturing technologies, and I could just see the single type of machine expanding what else we can do. Any last words before we get going?
Just want to thank you and Xometry. It's amazing and really encouraging to see companies like Xometry that have had so much success and that are contributing to, democratizing the use and the transition to production and the adoption of 3D printing in general. So really exciting collaborating with you, and hopefully this will be a routine exercise of keep updating the audience with the progress and the newer applications and new barriers that we're breaking with this technology.
Absolutely.
Yeah,
Right, well,
and thank you from my end as well. This is a great webinar. Thank you everyone for joining, and looking forward to the future ones.
Absolutely. Thank you all so much again. Have a wonderful evening, and again, thank you to the team at AMT. All right, have an awesome day.
Thank you.
Thank you.